All right, let's get started. Good morning, everybody. Hopefully you're ready for another exciting, interesting morning with your host, me, Dr. White, and chemistry. Now, a couple things. First of all, don't forget this Thursday will be test 3. I've already talked about it. There's an announcement on Blackboard giving the points breakdown. It will be on gases and solutions. And I will send out the password Thursday morning. Now, today I should mention, I'm going to go a little over. Usually I end at 10, but for your benefit, I'd like to end early because I got other things I could do, but no, you're more important. I'm going to go a little over. However, let's see how much we get done because there's certain things I want to do. I threw myself a little off schedule by about a half hour or 45 minutes time-wise because I felt it was more important to spend more time on the material on test 2, which is the hardest. And it looks like my efforts, or more importantly, your efforts, paid off. So, all right, what we're going to do today, I need to finish the solutions chapter. It'll only take a little while. After that, I'll talk about the lab. I should mention one of your colleagues last night pointed out, no, I shouldn't have had a V8. I made a mistake on the ideal gas law, where I gave some numbers for formulas and I messed up. Haste makes waste. By the way, I think I'm the only instructor who, because I don't like Zoom, I've been creating my own labs for you, which does take time, but I think it's better for you, which is why I spent a good part of yesterday finishing up the solutions lab I'll talk about. So I'll talk about the solutions lab. By the way, the ideal gas law lab, because I made a mistake in some of the numbering, it's not due today. If you can get it in next couple of days, that's fine. Go back and check it. All right, let's get to work. All right, what I'd like to finish up in solutions is talking about boiling and boiling points. Now, I think you're all familiar with, if you take a pot, put water in there, put it on your stove, heat it up, you'll see bubbles coming up, and you know you're boiling water. And I think I'm going to assume, even though you should never assume, but I'm going to assume each and every one of you at some time in your life has seen a pot of boiling water. I think that's a good assumption. All right, but what is boiling? And it doesn't have to be just water. Boiling is a special form of evaporation. Evaporation is when a liquid becomes a gas at a temperature where it should still be a liquid. A special form of evaporation conversion from liquid state to vapor state that occurs in a body of a liquid through bubble formation. The bubbles contain the vapor, the gas of the liquid you're boiling. Now, we have a special thing called the boiling point of a liquid. And that's the temperature at which the vapor pressure of the liquid, in other words, the gas coming from the bubbles, equals the atmospheric or external pressure exerted on that. And normal boiling point happens at 1 atmosphere, 760. Now, I'm not going to ask you definitions. Forget about the intermolecular. Oh, thought I had more slides. All right, time to go to Dr. White's whiteboard. Thumbs up, people. Do you see the whiteboard? Thank you. All right, let's get to work. This is stuff you should know. Great moments in why Dr. White will never be an artist.
We actually don't see the whiteboard.
Uh-oh, I thought you did. Thank you, whoever. Let me correct that. Now do you see the whiteboard? Let me ask my thumbs up people. Can everybody see my, no? Any better? All right. Zoom doesn't like me. It's getting back at me for some reason. Not really. All right. Once again, Dr. White will never be an artist. Now, here's a beaker of water on a hot plate. Now, after a while, you'll see little bubbles in here. And those bubbles contain water as a gas. And they come to the surface, collapse. So you'll have now above here water in a gas form, and we call that water vapor. And as you know, any gas has a pressure that you can measure. And when the vapor pressure, the water gas pressure equals atmospheric pressure, we call that the boiling point. In the case of water, at 1 atmosphere, it's 100 degrees C or 212 Fahrenheit. Now, here's something important. If the atmospheric pressure decreases, then the boiling point, this you should know, decreases. And how does the atmospheric pressure decrease? You go higher in our planet. The higher you go elevation, the lower the atmospheric pressure. I'll abbreviate. It's supposed to be an M. So what happens when you go to Denver? Well, Denver is called the Mile High City because it's not at sea level. And in Denver, the atmospheric pressure is lower than 760. And because of that, the boiling point of water is lower. I think it's about 95 Celsius, but don't quote me on that. But if you've ever been to Denver, know people live there, if you buy noodles or rice, you'll see on the package an extra label, you have to cook it longer. If you're in Chicago and you're cooking, say, noodles, and you cook it for 8 to 10 minutes, in Denver, you have to cook it longer. Why? Because you're at a higher altitude, lower atmospheric pressure. The vapor pressure of the water boiling can be lower, so you can add less heat, which means lower temperature. Because it's at a lower temperature, you're boiling water, to cook your noodles, you have to cook it longer. Now, where is the highest place you can think of in the planet? The Himalayas. Or if you go to Kathmandu, which Dr. White never has and probably never will go, but it's very, very, even off the screen altitude, that means the atmospheric pressure is very low. And because of that, the boiling point of water is very, very low. And if you've ever seen documentaries about people who go to the top of the Himalayas, the people who live up there, I think they're called Shirka, I'm not sure, but the people there, because they're living at a higher altitude, their body is used to the less atmospheric pressure, less oxygen they're breathing. But when other people like you and me go there, if we did, they usually have to bring some oxygen to help them breathe or go a certain height, stay for a couple days to get their body acclimated to the lower atmospheric pressure. But what that means is the higher you go in the planet, higher elevation, the lower the boiling point, because of the boiling point is that the temperature of a liquid when its vapor pressure equals the atmospheric pressure. And you should know that. And one other thing I should point out, when something evaporates, goes from a liquid to gas, it takes energy. And that's why you could, let's put it this way, men sweat, women perspire, because the liquid on your body evaporates and cools you off. Now, if you go out today in this weather where the humidity is going to be super high, it's harder for your body to evaporate the moisture, perspiration, women sweat, men. And that's why in this weather, if you play tennis or out there exerting yourself, it feels much worse. You tire quicker because your body can't cool it down. You should know about evaporation and boiling. And the key thing, everybody see the screen now? Whiteboard, thank you. You should know this. All right. That the higher the elevation, the lower the atmosphere, and the lower the boiling point. When the atmospheric pressure is low, the boiling point is low. Now, the opposite is also true, and this won't be on a test, but just why are you learning chemistry? Well, how many of you are familiar with a pressure cooker? If I look around, everybody is raising their hand or their thumb, some of them. And that's a device that you seal in everything and you cook things in it. And it cooks things faster. Now, Dr. White will never use a pressure cooker because I work with gases at very high pressures. I don't think they're safe, but that's my personal opinion. But they've gotten a lot better over the last decade or two. Well, pressure cooker holds everything in there. Therefore, the pressure inside is higher than atmospheric. Therefore, the boiling point of liquid in there, water, is higher. So when you heat that on your stove, unlike putting something in boiling water without pressure, 100 degrees C, boiling point or temperature, the temperature is higher in there. Therefore, that's why it cooks food. So next time you're using your pressure cooker, you understand that the temperature is higher in there because boiling point equals atmospheric or pressure. Well, inside there, the pressure is higher, so you need more energy to get the boiling point of water. And that's how it works. All right. The stuff on intermolecular forces, ignore. I'm not going to cover that. All right. What I like to do now is go through the lab you'll be doing today. It's a fun lab. Since Zoom has been playing games with it. Everybody see the lab on the screen? Thank you. This is going to be the Chem 1211 signal. Thumbs up. All right. Today's lab deals with solutions and colloidal dispersions, which you've been learning about. And as you know, a solution is two or more compounds mixed together to form a homogeneous mixture. That means it's the same throughout, in which none of the components or compounds change its chemical composition. They don't react. Now, a couple important concepts for today's lab. One in the solutions is molarity. And molarity is a key way of measuring concentration, how much of a solute is in a solution. And molarity is defined for this class as moles of a substance per 1,000 milliliters. Now, another important concept for this lab is the rule of thumb that states like dissolve like. And this means that polar compounds are soluble in polar solvents, tea break, and nonpolar compounds are soluble in nonpolar solvents. If you mix polar compound and a nonpolar solvent, it won't be soluble and you won't get a homogeneous mixture. And I should have put, instead of non-homogeneous, it really should have written heterogeneous. Well, next version of the lab, I'll change that. Now in today's lab, you're going to be using water as a polar solvent and an organic molecule or solvent, liquid at room temperature, hexane, is a nonpolar solvent. Now, another thing we'll be talking about in today's lab is a colloidal dispersion. And at first glance, you say, oh, that's a solution. No, a colloidal dispersion is not a solution. They're formed when one or more compounds is dispersed, not dissolved, in another. Since small particles of one substance is dispersed and not dissolved in there, colloidal dispersions scatter light, pass through there. In other words, don't let light pass through it. And solutions do not scatter light and let light pass through them. It's time for, once again, Dr. White gets to play with his flashlights. And if you notice, my tea is a solution. How do you know? The light's going through. Now, if I had something like milk and I put it through, so let's say my hand was a glass of milk. Oh no, it scatters the light and the light won't go through. Pretend my hand was a glass of milk. And you're going to be doing these things in today's lab. And hopefully you're seeing the lab again. Thumbs up, people. Can you see the lab? Thank you. All right, so in today's lab, you'll be investigating solutions and colloidal dispersions. Let's look at part one. Part one, you'll be investigating the rule of thumb, like dissolves like. And you'll be mixing various compounds in water and hexane to determine the polarity of a compound. Is it polar or nonpolar? Now, in part 1A, you're going to be using water solvent. And what you'll do if you were in the lab, I've got to see if, I don't know if there's anything on YouTube, but anyways, you take 6 clean test tubes, each one add 2 milliliters of water. DI means deionized water, which is what we use in the lab. Next to each test tube, add a small amount of the following, I didn't write down small amount, of the following compounds: methanol, paraffin wax, naphthalene, which is just mothballs that are crushed. Mothballs are really naphthalene, potassium chloride, toluene, and ammonium chloride. Now you mix the two together on a thing called a vibromixer. And a vibromixer is this little vibrating plate of rubber that mixes a test tube really good. And then after you do it for about 20 seconds, by the way, vibromixers are fun to play with. But anyways, you place the test tubes in the test tube holder. And then after 2 minutes, you'll pick up the test tube and examine, is it homogeneous, the same throughout, are heterogeneous. Another way of saying that is if it's homogeneous, the two are soluble. If it's heterogeneous, not the same throughout, the thing you mix in water is insoluble. Remember, like dissolves like. And record your results for each test tube. At the end, put the contents of that in a waste bottle and clean your test tubes. Now, in part 1B, you'll do the same thing with the same chemicals, but instead of water, which is polar, you'll use hexane, non-polar. And here, you'll do the same thing. DI shouldn't be here. I forgot to eliminate it. There's no dihexane. All hexane is deionized. But anyways, in 6 clean test tubes, you add 2 milliliters of hexane. And next, add each of the same following compounds: methanol, paraffin wax, naphthalene, potassium chloride, toluene, and ammonium chloride. You'll mix it with the vibro mixer, wait 2 minutes, and look at the test tube to see if it's homogeneous, soluble, heterogeneous, insoluble. And you'll record your results. Since we're online, you're not in the lab, oh, look, you did it already. And notice when you add the methanol to water, it's soluble. Paraffin wax is insoluble, and you can look at the rest on your own. In hexane, when you add methanol to hexane, now it's insoluble, and paraffin wax is soluble, and you can look at the rest. That's part 1. Let's go into part 2, molarity. In this experiment, you'll determine the molarity of an aqueous sodium chloride solution by removing the water and determining the weight of the sodium chloride. How can you do this? Well, first of all, when you make a solution, neither compounds you mix together are changed. So if I can remove one of them, the other will be left behind. And you do this by heating the solution. And by measuring how much sodium chloride is left behind and how much water you evaporated, you can calculate the molarity of this unknown solution. And what you'll do is, in an evaporating dish, you'll weigh it. Then you'll measure out 5 milliliters of the sodium chloride solution with a graduated cylinder, pour it into the evaporating dish. You'll weigh it again and record the weight. Next, you'll put the evaporating dish over a beaker of boiling water. Be careful, don't touch the hot plate or you'll burn yourself. I always tell students that when they're using a hot plate in the lab, because they will burn themselves if I don't tell them. But anyways, you place it over to boiling water, and the boiling water heats up the water in the solution in the evaporating dish, and it evaporates, disappears, actually goes into the air. And you do that until all the water is gone, the liquid. Then, to be sure you got it off, you take the evaporating dish and put it on a hot plate, and you heat it until you no longer hear the sounds, and you actually hear this snap, crackle, and pop, sort of like Rice Krispies and melt. And then when that stops, you remove it and put it on a wire gauze screen so you don't ruin the bench top, and you let it cool. After it's cooled, you record the weight and rinse out the evaporating dish at the end with water down the drain. Now, the data for that, here's the weight of the dish, empty. Here is it with the solution. Here is it after you've taken off the water. Now, these things here, you have to do calculations. Instead of using numbers, which confuse people, including Dr. White, messed up, I use letters. Here's A, B, and C. And for the weight of the sodium chloride in the sample, which is grams, D, it's C minus A. And the moles, E, is D, this weight, divided by the molecular weight of sodium chloride. I'll let you figure that out. And then the volume of the sample, you measured 5 milliliters, but the actual water is F, which is B minus C, and the molarity H is E, this times 1,000 divided by F, this one. And that way you can do the calculations, fill in the numbers here. And finally, my favorite part, Dr. White loves colloidal dispersions. And this part of the lab, you will determine if a mixture is a solution or colloidal dispersion by using a flashlight. Yay, I like flashlights. I've liked them since I was old enough to know, ooh, that's a flashlight. I had my first good one when I was 5. Deep break. All right, so what's the procedure? In 6 separate beakers, hopefully I counted right. Yep, 100 ml beakers, you'll fill it half full, which each of the following products. We'll do 7-Up pop. Remember, pop is the material in a can or bottle that has little bubbles. I think you're all familiar with maybe the product 7-Up. Also mustard, mayonnaise, ketchup, dangerous chemicals there, vinegar, and rubbing alcohol. And you're going to find out by putting, for each beaker, after you put in about half full of each one of these, you'll take a flashlight and shine it, just like this. I get to play with my flashlight again. Take your flashlight, hold it to the beaker, and then does it shine through or not? By the way, this is a beaker mug. All right, it took a little longer to switch. Everybody see the labs now? Thank you. And since you're not going to be able to do this in the lab, I've done it for you. And here's the results. The substance and the light pass through, yes or no. Now, for this lab, here are the questions at the end you need to answer along with the data for the molarity and upload this as a PDF file. And that's the lab. Any questions on the lab? This is available to you both as either a Word document or PDF on the assignment area or in the assignment area of Blackboard. All right, moving on.
Which one of them is, sorry, which one of them is the one that you can shine the light through? Would that be the solution?
Right.
Or the
When you can see light coming through, oh, I'm going to use my red one. See the light coming through? That tells you it's a solution. If you don't see light coming through because it's a dispersion, colloidal dispersion, and those particles block the light and scatter it, then you know you have a colloidal dispersion. If you take a glass of milk, unlike my tea, and put the flashlight, you won't see any light come through because the particles are scattering the light and not letting it go through. I'm getting pretty good at my hand signals. Does that answer whoever answered that question?
Yes, thank you.
You're welcome. Remember, in my class, there's no such thing ever as a dumb question. All right, what I like to do next is go through the review for test number 3. Hopefully you all see it on your screen. I'm going to ask thumbs up, thank you. All right, what you see is available for you as a Word and PDF file in the lecture section of Blackboard, so you can go back and look at it. Let's go through important things you should know. We talk about gases. You should know. Also, let me remind you, in the lecture section of Blackboard, I have important information for test number 3. You should look at that because that's stuff you don't have to memorize, but you do have to know how to use. And I give you this right here and this here. All right, first of all, pressure. You should know 1 millimeter mercury equal 1 torr, and 7/6, that should be millimeters, not inches. Or no, that should be torr. I'll have to change that right here. This should be torr. All right. Anyways, 760 torr equals 760 millimeters of mercury, 1 atmosphere. I know it's right on the important information. I just have to change this again. I'll do that later today. Don't forget, in gases, you measure Kelvin more often than Celsius, or Celsius, and Kelvin equals degrees C plus 273. Now, I taught you Boyle's law. P1 times V1 equals P2 times V2. In a little while, I'm going to go through some of the problems I should get to today on the gas law or gas problem set. And Boyle's law, remember, P1 is the initial pressure, V1 is initial volume, P2 is the final pressure, V2 is the final volume. You'll be given P1 and P2, P1 and V1, and then one of these two, and you'll be asked to find the other. And remember, I taught you how to solve for a variable. We'll go through that in a little while. We go through the problem set questions or answers. All right, next is the ideal gas law, PV equal nRT. This will be given to you. Remember, P is pressure in atmosphere. You're always going to get it in millimeters of mercury or torr, so you'll have to convert it. V is in liters. I'll always give you, if I give you volume, will be in liters. Mole is, N is moles, but you'll get grams. And for test 2, you learn how to go from grams to moles. Important information, I do put that at the end for test 3 in case you forgot it or do forget it. Temperature is in Kelvin, but you'll always be given that in Celsius. So you have to convert degrees C plus 273. And finally, R is the universal gas law constant. For this class, we're using these units, and it's 0.0821. Remember, this is a calculated number, R, and therefore 821 is 3 significant figures. Tea break, which is a solution. All right, I taught you Dalton's law of partial pressures. The total pressure of a mixture of gases is the sum of the partial pressures, P1, 2, 3, or whatever, of the components of the gas. I won't ask you, but the partial pressure is the pressure of that component of the mixture of a gas if it were alone. Now, I just talked about boiling, and boiling point of a liquid is when vapor pressure of a liquid equals atmospheric pressure. And the higher the atmosphere, the altitude on Earth, the lower the atmospheric pressure, therefore the lower the boiling point is. So if you go to Kathmandu, which I never will be, but for those of you from my generation, I forgot whose song was about Kathmandu. But anyways, it was a famous rock song. But anyways, the boiling point of water is lower than here in Chicagoland. All right, one other thing I forgot to talk about, remember, PV equal nRT tells you when to check your car tires. When the temperature is very low, V, N, and R in your car tire isn't going to change, but if the temperature drops really low in the winter, the pressure will go real low in the winter. PV equal nRT. Now, it's getting pretty warm out there, but not like it was back in 1995 and even 2012, but really 95, I remember, because we had for 2 weeks, daytime temperatures were all above 100 degrees Fahrenheit, not the feel, the real temperature. And you saw on the highway, trucks and cars pulled over with blowouts because they didn't do the following. PV equal nRT tells you temperature goes up, pressure goes up. And if your pressure goes up too high in your car, it goes boom, just like a balloon popping. All right, let's talk about solutions. You should know that a solution contains a solvent, which is the component of a solution present in the greatest amount. All other components are called solutes. So again, the solvent of a solution, which there's only one, even though nowadays some people have changed that definition, but I don't, most chemists don't, is the component of a solution present in the greatest amount, and all other components are called solutes. Now, as you learned from today's lab, colloidal dispersion is not a solution, and it scatters light because the particles are suspended in a liquid. Next, you also learned went over today for today's lab, light dissolves light. And although most of the things I'll be teaching you, this is probably one of the more important things for your daily life. And like dissolved light means like solutes are soluble in like solvents. And what that really means is polar solutes are soluble in polar solvents. Nonpolar solutes are soluble in nonpolar solvents. Water, alcohols, and salts are polar. Vegetable oil, Vaseline, gasoline, baby oil, grease, and dirt are nonpolar. Oh, look, Dr. White's being subtle again. Know this. Now, there's certain definitions for solutions you should know. One is the solubility of solute. That's the maximum amount of a solute that will dissolve in a given amount of solvent. And you should know that. Also, that means is if I have reached the solubility limit of a solution, I put one more molecule, it will precipitate out. That means forms a solid at the bottom. And that's occurring in a saturated solution that contains the maximum amount. So you can't dissolve anything more in a saturated solution. If you try and it's a solid, it just floats to the bottom. So saturated solution, you should know, is a solution that contains the maximum amount of solute that can be dissolved under the conditions that which the solution exists, mainly temperature and pressure. Now, a dilute solution, you should know, is a solution that contains a small amount of solute relative to the amount you could dissolve. The opposite of that is a concentrated solution, and that's a solution that contains a large amount of solute relative to the amount that could dissolve. Now, a very important definition is aqueous solution. And when you see the letters AQ in a bracket, that means it's an aqueous solution, which means it's a solution which water is the solvent. Aqueous, AQ, water is the solvent. Now, I talked about concentration, how much of a solute is in a solution. And the important one I want you to know, the other two I talked about were interesting, but for test number 3, molarity. You should know molarity, which is indicated by a capital M, of a solution is a ratio of the given moles of a solute per liter of solution. And you'll be given this important information. And molarity is moles of solute per 1 liter, but in the lab we use milliliters. 1 liter equals 1,000 milliliters. So you should know, and this will be given to you in important information, so you don't have to memorize it, but molarity is moles of solute per 1,000 milliliters solution. And I showed you yesterday the 2-step, and I'll go through it again tomorrow, of calculating how many grams you need to make a certain solution, and you have to do that in 2 steps. First step, the milliliters are converted to moles of solute. Second step, which you learned for test 2, is you take the moles and convert it to grams. In case you forgot, 1 mole of an element equals the atomic weight of the element in grams. 1 mole of a compound equals the molecular weight of that compound in grams. the molecular weight of a compound is the sum of all atomic weights. Hopefully that helped you. By the way, how many people like my reviews? Give me a thumbs up. I'm looking at everybody. All right, well, I guess it works. Good news for test 4, I'll do the same. If you look at the syllabus, you'll see the very last week, I'm going to review the whole semester. And that's why students do good on my final, because if you show up or watch me on YouTube, remember Dr. White's a YouTube star, you get a couple hours of review and study with me, Dr. White, in addition to what you do on your own. Let me just see what's happening. Andrea, thank you very much. And all of you who agree, thank you. Don't tell anybody, but I do things to help students get good grades in my class. Why? Because Dr. White's selfish. If you get a good grade in my class, guess what? You've learned chemistry. Shh, don't tell anybody that. All right, let's go through next. Hold on one second. I know I can't find it. Hold on, I gotta clean up some things. I got too many windows open. No, I can do it. All right. Once again, Dr. White's going to ask, thumbs up, people. Can you see chapter 11, gas? Thank you. I wish Zoom had a better interface because once you click on it, it doesn't actually show you it's actually on there. All right, let's look at important practice problems for chapter 11. The first thing you should know, let's see if I can, no, I'm on, that 1 millimeter of mercury equals 1 torr. Therefore, how many torr is 41.5? Figure out torr, that's what you're trying to find. You're given this. It's time to use, oh, I got to do it. I've gone almost a whole 45 minutes. I haven't done this. It's time to use your good buddy, good friend, unit analysis, and it's been my good buddy and good friend for many decades. Never fails me. And it shouldn't fail you. All right, so here's what you have to start with. You're trying to get to torr. You put whatever you're trying to get to on top, get rid of underneath. It's 1 to 1. These are exact numbers, same answer. But now, let's look at this. How many atmospheres is 741 torr? You're trying to find atmospheres. You're given torr. On important information, I got it right here. Note, 760 torr equals 760 millimeters of mercury equal 1 atmosphere. This is a definition. Therefore, 760, 761 are exact numbers and do not play a role in determining significant figures. Now, here's what I'm starting with. I'm trying to get to atmospheres. Use unit analysis, your good buddy, your good friend. What I'm trying to get to goes on top. What I'm trying to get rid of goes under here. And where do we get these numbers from here? 1 atmosphere, 760. This is 3 significant figures, exact number, 3 significant figures is my answer. Now, if we look at number 4, it's a little different. How many torr is 1.237 atmospheres? And here, what are we trying to find? Torr, which is a measure of pressure. These are all pressures of gases. What are we given? 1.237 atmospheres. Therefore, here's what we have to start with. What units am I trying to get to? Torr. Use unit analysis. If you have a ratio that will convert this to this, what goes on top of the ratio? Torr, what you're trying to get to. What goes underneath, in this case, atmospheres. Where do I get these numbers? Right here, and this will be given to you, important information for Thursday's test, and that's 1 atmosphere equals 760 torr. These are exact numbers. This is 4 significant figures. My answer should be 4 significant figures, and it is. You should know how to do these conversions and how to use 760 torr equals 760 millimeters of mercury equal 1 atmosphere. All right, let's look at number 6. If a balloon has a pressure of 658 torr and a volume of 1.894 liters, what's the pressure of the balloon if the volume is increased to 5.133 L is liters volume? So what are we trying to find? The final pressure, P2. What are we given? An initial pressure, P1. What are we given? An initial volume, V1. What are we given? The change to new volume, V2. Now, if you notice, the only units or measurements you're being given are pressure and volume. And as soon as you see that, you know that P1 times V1 equals P2 times V2. Boyle's law. You'll be given this. You'll also be given what is P1, V1, P2, V2. Now in this one, we're trying to solve for P2. Therefore, when it's multiplied times something else, how do you get rid of V2? You divide by it. Whatever you do on one side, you have to do on the other. Anything divided by itself becomes the number 1, P2, because 1 times P2 is P2. And here we have this. I like to rewrite it. You don't have to. P2 equals P1 times V1 over V2. Put in the numbers we already took time to figure out. Notice you should use your good buddy, your good friend, unit analysis. Notice liters divided by liters comes to number 1. And the only units we're left with is torr, which is a good thing because that's pressure. And for multiplication division, remember, and a lot of you lost points on test 2, so remember to do this for test 3. You get the same number of significant figures, wrong thing. You get the same number of significant figures in your answer that the number that you're multiplying or dividing that has the fewest significant figures. So let's look here. 3 significant, 4, 4. What's the lowest number? Time's up. Hopefully all picked 3. So notice my answer has 3 significant figures. Let's do number 11. If this were on a test, it would be 15. Yes, 15 points. 15 points. All right, a tire contains 25.6 grams nitrogen gas, N2, at 26 degrees C, 705 torr. What is the volume of the nitrogen gas in the tire? All right, remember, 15 points. Is anything changing? No. You're given a weight that doesn't change, temperature that doesn't change, and pressure that doesn't change, and you're asked to find the volume. Immediately that should tell you 15 points. It's PV equal nRT, the ideal gas law. Now, if we look over here, what are we being asked to find? Volume. What are we given? The weight of nitrogen. What are we also given? 705 torr is a pressure. 26 degrees C is a temperature. You'll be given R. Again, look for the important information so you see you don't have to memorize these. 2 years ago when I taught this course, I'd have students memorize it, and I finally decided it's better to teach students what, how to use stuff, not to test how good their memory is. And now we have PV equal nRT. What are we looking for? V. We have to get rid of P. When two things are multiplied, you want to get rid of one of them, you divide by it, because anything divided by itself is number one, and 1 times something is that something. So I divide by P. Whatever you do on one side, you have to do on the other. This divides, P divided by P is 1, V, and this side I have nRT. Now, pay attention. This is a common mistake students make with this type of product. Don't, please. Did I make a mistake on that one? Someone said 2.43. Well, we'll come back to that. Am I off by a factor of 10 on this? Sorry about that. All right. Now, the mistake students make is you've got to have the right units for N, T, and P. N is moles. You got grams, so you have to convert grams to moles. Moles, how do you do that? Here's what I'm starting with grams. I want to go to moles. Remember, unit analysis, moles goes on top of the ratio, grams go underneath. Where do you get this? 1 mole of a compound equals its molecular weight. And the molecular weight of nitrogen is sum of all atomic weights, 2 times 14.0. Remember, on test 3, like test 2, use all atomic weights to 3 significant figures. Nitrogen is 14.0 times 2, 28.0. And here, 4 significant, exact number, 3 significant. Now, this is one of those problems you can round off at each step. I do, or wait till the end. I calculated both ways. Now, next, pressure has to be in atmospheres in this. It's in torr, so you have to go from torr to atmospheres. Use unit analysis, the conversion factor, atmospheres goes on top, torr goes underneath. 1 atmosphere, 760 torr. You'll be given that. That's how you know the numbers. These are exact numbers, 3 significant, 3. I now have my pressure in atmospheres. Now, temperature, it should be in Kelvin. I see so many times students just put 26 in there. It's wrong. This won't work unless temperature is in Kelvin. Kelvin is equal to degrees C plus 273. 26 plus 273, 299. Now we have N, we figured. We have R, which are given. You have temperature in Kelvin and the pressure, and students have just told me that should be 2.43 liters instead of 24.3. So I'll assume you're right. Dr. White's going home now. I am home. I can't do that. In a classroom, if I had said that, oh, I made a mistake, goodbye. I'm going home, but I am home. So be careful of that. But the way it's set up and everything. Now, important thing for test number 3. show your work for problems. If you make a mistake, but you show your work, I can follow it. Now, tomorrow, I will go through the solutions problem set. And if you look at the time, we're doing pretty good. All right, some people say I was right and some people don't. I'll calculate it later today and I'll post the email to all of you which is right. Maybe it's 5 million. No. All right. What I like to do right now is just take a little time and go into the next chapter. I'll go for about 10 minutes more, so hang in there. And this will keep me on track. Now, this will be for test number 4, and this chapter deals with, we're doing 15 before 14, because it makes sense, unlike in the book, but this will be better. We're going to be talking about chemical equilibrium and rates of reaction. And if you were reading the book, I'd be telling you, I'm going to put some stuff in here that's not in the book, but I think it's important you should know. Now, there's an important concept called the collision theory of reactions. And the question is, when you mix two things together, what happens to form a chemical reaction? Well, the collision theory is a series of statements that tell you that. And you should know this for test 5. First of all, in the collision theory, in order to have a reaction, reactant particles must interact. In other words, collide. That's why it's called the collision theory. And they must hit each other. So if I'm to have a reaction, I have this chemical and this chemical or molecule, they have to collide. And that's why it's called the collision theory. If that doesn't happen, no reaction. Let's assume I have a beaker here, one chemical in here, and I can hold them for the rest of eternity. They're not going to react. Now, if I mix them together, the molecules can now collide, and they could react if they're going to react. You should know that. The next part of this theory is activation energy, and this is very important. And what it means is colliding particles must possess a certain minimum total energy, which is called the activation energy, if the collision is to be effective. In other words, you actually react. It's another way of saying it, the amount of energy to break bonds of atoms of the reactants. That's from your book. I don't like that. Another one is activation energy. It's the minimum combined kinetic energy that particles must possess in order for the collisions to result in a chemical reaction. So what that means is I have two particles, they're coming together. They just go, think, nothing is going to happen. They have enough energy and they go, smash. Oh, that hurt. I'll do it again for you though. Smash. Oh, that hurt. No, not really. That means I'll have enough energy to form a chemical reaction. And that's an important concept. And the last one of this is, or second last, there's two more, collision orientation. Certain molecules, when they collide, must be oriented properly for the particles to react, unless they're small molecules or atoms. But for most reactions, this is true. And how do you envision that? Ta-da, my house key for my front door. Now, if I put it in the lock like this and turn it, I'll unlock the door. If I go like this, it won't go in the lock and I can't unlock it. Molecules are like that. If they come together the wrong way, they won't, but if they go like this, they can react. So the orientation, just like the key, has to be correct. And that plays an important role, especially many molecules in your body, such as your enzymes and other things that are reacting, have to be in the right orientation. By the way, I don't know if I told you, you know who's the greatest chemist of them all? Mother Nature. You know something? I think we caught up. I hopefully didn't go too quick. I think we're in a good place. So with that, I'm going to say goodbye. I'm done for today. If you need any questions, always email me. Don't forget my office hour. Don't forget the lab we're doing is on Blackboard, and the ideal gas law lab is, even though it's normally due today because of a mistake Dr. White made, bad Dr. White, you have extra time. With that, gang gesund, be healthy, be careful out there. I'll see you tomorrow, or you'll see me tomorrow if you don't have your picture turned on. With that, bye.